Welcome students in this video lecture, and today our topic is hexadecimal and octal number system. For hexadecimal number system, base is equal to 16. Therefore, the symbols that are used in this number system are 0 to 16 minus 1, that is 0 to 15. However, weights 10 to 15 are represented by A to F to avoid the repetition of symbols. Hexadecimal number system is an alphanumerical number system, and the number is represented by n subscript base 16 or n with the subscript h. This h represents hex number or hexadecimal number. For octal number system, base is 8. It implies that symbols that are used in it are from 0 to 8 minus 1, that is 0 to 7. It is simply a numerical number system where a number is represented by n with the subscript 8. For the hex system, the base is equal to 16, which can be written as 2 raised power 4. For the octal system, the base is equal to 8, which can be written as 2 raised power 3. Therefore, for these number systems, we have the base that can be written in form of powers of 2. As a matter of fact, we can have also the base is equal to 4, which can be also written in 2 raised power 2 form, that is also in powers of 2. So what is the consequence of these number systems which can be written in form of powers of 2? We can see this using an example as follows. Now we have taken 49 as a decimal number, and we will convert this number in binary, that is base 2, in base 4, in base 8, that is octal, and in base 16, that is hexadecimal number. Let us first convert this number into binary. So I have written the powers of 2 in descending order. So 2 raised power 6 is 64. 64 is greater than 49. It cannot be present in it. So we have to write 0 below it. Now 2 raised power 5 is 32. 32 is less than 49. It can be present in it. So we have to start from the higher powers of 2. So it is present in it. 32. Then we have 2 raised power 4. 2 raised power 4 is 16. 16 plus 32 is 48. So it is also present in it. Now 16 plus 42, 16 plus 32 is 48. We are left with only 1. So this will be present. The rest will be 0. So the binary form of 49 is equal to 110001. Now let us convert 49 decimal number in base 4. So we have to repeatedly divide this number by 4. 4 multiplied by 12 is 48. So 1 is the remainder. 4 multiplied by 3 is 12. So 0 is the remainder. So 49 decimal number is equal to 301 in base 4. Now converting this into octal, 49, 8, we have 6. 1 is the remainder. So 49 decimal is equal to 61 in octal form. Similarly, in the base 16, 49 divided by 16, we have 3, then 1 is the remainder. So 49 in the base 10 is equal to 31 in base 16. Now look carefully on the bases. For base 4, it is 2 raised power 2. For base 8, it is 2 raised power 3. And for base 16, it is 2 raised power 4. If we somehow replace each digit in the base 4 by 2 bits, because it is 2 raised power 2, what we get is 3 in binary form is 1 1, 0 in binary form is 0 0, and 1 in binary form is 0 1. So we will get the same result. Similarly, 6 in binary form is 1 0 1, 1 1 0. We have to write 3 here because in the octal number system it is 2 raised power 3. We have to replace every octal number by 3 bits. So 1 0 is 6, 1 is equal to 0 0 1. So again we get the same result. Now similarly, we have to replace each hexadecimal number by 4 bits because base is 16 and it is 2 raised power 4. So 3 in 4 bits can be written as 0011, and 1 in 4 bits can be written as 0001, which is equal to 11001 in binary form. So we are getting the same result in all of these. Now what is the consequence of this? The consequence of this is that if the base is in the powers of 2, we can interconvert and travel through these number systems using the binary number system. How this can be achieved is that we have to group bits. So for base 4, 2 bits are to be grouped. For base 8, 3 bits are to be grouped. And for base 16, 4 bits are to be grouped. And for similar higher orders of 2. while grouping, it has to be keep in mind that if the given binary number has integer part and fractional part, then while grouping from left side of the radix, we have to group from the LSB, append some zeros at MSB to form the complete groups. Similarly, for the fractional part, that is for the right side of the radix, we have to group from the MSB and we have to append some zeros at LSB to form the complete groups. To elaborate this, let us consider the following example wherein a binary number is to be converted into octal number. So this binary number has integer part and fractional part. So this is the radix, and on the left side of the radix, we have to start from the LSB and start forming groups of 3. So these are the 3 bits, 3 bits and 3 bits. Now this is equal to 3, this is equal to 3, and this is equal to 4. Similarly, on the right side of the radix, or for the fractional part, we have to start from the MSB. So and start forming the groups of 3. So this is the 3, group of 3, group of 3. So this is equal to 1, this is equal to 5, and there is 1 left. So we have to append some zeros in it, and this is equal to 4. So this binary number in hexadecimal is equal to 433.154 with the base 8. Similarly, you can directly convert this binary number into the base of 4, into the base of 16, or into any base that is power of 2 by grouping of the bits. Now, how do we convert a hex number into octal number? We know that both these number systems have directly link with the binary number system. That is, for a binary number, we make a groups of 3 bits, and for a hexadecimal number system, we make a groups of 4 bits. So what we can do is that we convert this hexadecimal number into binary number, and this binary number is then converted into octal number. So this is how we convert hexadecimal number into octal number. Or for that matter, any base which has a power of 2 can be converted to any other base which is the power of 2. Now consider the following example where CAD in hexadecimal is to be converted into octal number. Now what we have to do, we have to first convert this hexadecimal number into binary number. How we do so is that we make the groups of 4 bits. That is, C has to be represented into group of 4 bits. So C can be represented as 1100, A can be represented as 101, 1010, and D can be represented as 1101. Now after that, what we need to do, we have grouped C, we have represented C as 4 bits, A as 4 bits, and D as 4 bits. Now we need to reform the groups, but this time the groups must be 3 to convert the binary back to the octal. Starting from the LSB, we get following groups of 3 bits. Now 101 can be represented as 5, 5, 010 is the representation of 2, 110 is the representation of 6. So CAD is equal to 6255 in octal number system. This is all for this video. Thank you.